Heyo, it's chemistry time. Welcome to day 72, where we're going to take a look at these things called ice charts, hence the A plus B breaks C, technically, and a further look at endo versus exo with the energy diagrams. No, doesn't look familiar at all. Anyways, vanilla ice, baby. Anyways, that'll make more sense later. Here's what we're going to do. I'm going to get rid of my head. You're going to draw and explain why the rules for KQ versus Q are what they are. Make sure that you involve that with this thing called reaction direction, right? And then, of course, you're going to solve this problem. If you really understand that, that should be a breeze. So right now, you should pause me, write down the questions in your ETD, and give them a whirl. And then we'll take it on together. Sweet, I'm back. If we look at this, of course, we got to know about this thing versus KEQ versus Q rules, which are very, very handy for predicting the future. Now, if we look at this, the nice thing is KEQ and Q are very, very similar. If we look at KEQ is just the ratio of the products versus the reactants when it's at equilibrium, right? That means specifically that's when it's making and breaking products and reactants at the same rate. That is the dynamic equilibrium that runs everything in the universe, right? Now, let's say that I take a picture, my Q, and I find out my Q is exactly the same as my KEQ. Well, that simply means that the ratio of the products and the reactants whenever I took my picture was exactly the same. So that tells you that it's making and breaking products and reactants at the same rate. It's at equilibrium, right? Now, why is this? This is because of a simple thing. They're at equilibrium because they have the same number, if you look at those piles, of collisions between the reactants and the products. And that's why they're making and breaking reactants and products at the same rate. It's all about collisions, right? They're hitting each other at the same rate. They can break at the same rate. Then, of course, I can take my pictures at other times. I have my KEQ, which is always going to be the same at the same temperature. And I have my Q when I find out that my KEQ is greater than my Q. Well, we're just going to use the same simple old KEQ, right? Let's say it's got a KEQ of like 1 or something like that, where they're pretty equal. If I have a Q that, of course, is less than it, right, that means that there's a smaller amount of product. Just think about the top. That means the reactants are bigger. So that means this thing is not at equilibrium, and instead, the language we use is we say it's going to favor. Which direction will it favor? Well, it's going to favor the forward reaction. Now, that makes complete sense, because if you think about this is going to favor the forward because there are way too many reactants. They're going to run into each other and create products. So that's, of course, going to make up for the deficit in the products, which aren't colliding enough. So this is going to favor the forward reaction to make more products because you haven't made enough. Now, this is because, of course, if you just look at those piles, there are more reactants to collide, and those reactants will become products, right? Now, keep in mind that there are still products that are colliding to become reactants because, of course, it's an equilibrium system. They can all collide. They're in the same vessel, but there's more reactants, so they're more likely to collide to become the products until it balances out and reaches that nice equilibrium part of it. This, of course, would be a KEQ that's greater than my Q. I can also sometimes take my picture and find out that my Q is greater than my KEQ. Well, if this use that same lame old KEQ, which is typically not 1, right? But we'll use it for simple. If my Q is bigger, that means it's made more products. There's a little bit of reactants left. So who's going to run into each other more often? Hey, it's the products, and they'll become reactants. Reactants will still become products, but not at this faster rate. That's why there's a lot more products being converted into reactants because there's too many of them. So this would be a reaction that would favor, if it's a Q that's greater than the KQ, it's going to favor making reactants. That's the reverse reaction. And that reverse reaction is going to make more of those products. Right? Why is this? Most important question, because there's more products colliding to become reactants, right? Hey, this is like all about collisions. If you just think about traffic jams and collisions, which is why we did gas laws first, right? You can easily figure out what a reaction is going to do. If there's more of something, it's more likely to collide and push in the direction away from that collisions, right? It's like reducing stress or something. Now, what did I just do here? I used claim, evidence, and reasoning. I predicted what would happen and what it would favor, and I explained why. I guess that's a good way to do science. Cool. If we look at the next one, here's how we put that into practice. What do I need to find? What I need some Q, and then I need to predict the direction. It wants me to make that prediction. So finding Q is pretty easy. You just do it just like a KEQ. You put your products over your reactants. These are both gases. So there's my N2O4, nice brown gas. And then at the bottom of that, there'd be the NO2, nitrous oxide, and that'd be squared because there's two of those. Then I look and say, okay, those are molarities. I'm going to plug them in, right? I got a 2.21 for the molarity of my N2O4, 2.21. And then I got an 8.78 times 10 to the negative 2 for my NO2. And just looking at the negative 2, you can see the bottom is smaller, right? So I've got this, what I would do with this is also square it. I've got this fairly big number, 2.21, over this thing that's really, really tiny, like 0.007708804, right? So just looking at that right away, you can see that this thing's going to have a bigger top. It's a big Q. So this means that my Q is going to come out to a whopping 287 with 3 siggy figgies. That is the Q. That's the first part you had to solve. Then I got to predict what will happen in the future. How do I do that? I compare it to my KEQ. Well, it tells you the KEQ. At this temperature, the KEQ is 4.85, which is a big number. But 287 is a lot bigger, so that means that Q is larger, which means when I took my picture of this thing, it had a huge pile of products and a little pile of reactants. So who's more likely to run into each other? The products, and that's going to favor shoving it in the reverse reaction to make those reactants. It's still going to destroy some reactants and make products, but it's going to make a lot more reactants to get itself back to equilibrium, right? So if we look at this, if we ever have a Q that is greater than our KEQ, it will always favor, and that's the language you want to use, the reverse reaction. And that makes sense because that's going to make more reactants, right? And that means, of course, it's going to make more of these things called NO2 because a lot of them didn't get made, right? This is because, of course, there are more products. On a test, I'd want to call them like, the N2O4, the gas thing. There's more of those products that can do an important thing. They can collide. That's why there's a bigger pile of them. Now, if we look at what's going on here, of course, my Q, I just figured out is greater than my KEQ because my KEQ is a big number. It's got a pile about 4.85 times bigger than the reactants, but you can see that I got a pile that's 287 times bigger. So that means that it's going to destroy it until it reaches equilibrium. It's making and breaking them at the same rate. And I did this beautiful thing called claim, evidence, and reasoning because basically I made a prediction, I used numbers, and I supplied my scientific reasoning. I even drew a picture that shows that I can qualitatively think about this. Awesome, doing science. Now, cool thing is you would normally go after that Phet reversible reactions, which of course is linked onto this, and you're going to explore it on your own. What we're going to do right now is take a look at that together and figure out what some of the big ideas of that thing are. So I'm going to bring up the simulation. And when we do that, we can see a couple things. One, there's no particles here, so that's why it's absolute zero. There's no temperature. I'm going to add in, say, 50 particles because I feel like it, right? You can see that once I put them in the chamber, those are my reactants, and these are my products. And I can convert reactants into products if they collide and have enough energy to get from reactants to products. One thing I can also notice about, there goes another one. Hey, which direction are we favoring? The forward reaction, because there's more reactants, A's colliding, right? Things I can change about this. One thing I can change is I can change this weird ruler, this gate. You can kind of think about this like a pickleball court. I just went from pickleball, and now I'm playing volleyball. Hey, I'm changing the amount of activation energy. If it's really high, then the reaction can't actually happen unless you increase the amount of energy. I can do that by heating it up. And you'll notice that when I do that, both sides start to move faster, right? But this side's not moving as fast as that side. So the other part of this that I can change, of course, is I can take heat away. And when I take that heat energy away, you can see that they move slower. They have less kinetic energy. And the reaction kind of slows down. It's kind of like why we cook food, right? The weirdest and coolest thing about this is you can also change the height of the actual gray bars, the levels. Now that shows you an important thing. When I did that, they moved slower because, I turned their kinetic energy into potential energy. They're now at a higher energy level. That can be done with the reactants or the products, right? And the cool thing about this, of course, is I can continue to cool that down. And as I do that, they move slower and slower. And that means the reaction is less likely to happen. I wonder why we use Bunsen burners in class and stuff like that. Now, other cool things that we can do with this is we could change this activation energy, we could lower it, and we could increase energy. How would we do that? Well, the thing that changes that, of course, is called the catalyst. Catalysts make it easier to go in either direction. They lower the activation energy. And of course, if I increase the energy enough, well, I can get them to go either way, right? Now, one thing you can notice is the forward reaction is pretty darn easy to do right now because there's very low activation energy. How else could I make more B besides adding a catalyst? I could add energy by making it faster in terms of the collisions of those reactants. Or, of course, I could do a crazy thing. I could say, okay, that's not enough A. They're not colliding enough. I'm going to add in 100. Whoa, if I add in 100, A is more likely to collide, and that would favor the side that has more collisions. So it's going to favor pushing towards the product side because A is colliding more often. So I can change the concentration of my reactants. I can change the activation energy with a thing called the catalyst. And I can also change the amount of energy in the system by heating or cooling it to favor it. You can see that this one is definitely favoring the downhill battle because the forward reaction is exothermic. And you can notice that some of their potential energy gets turned into the faster kinetic energy of the lower potential energy products. So this really is about transforming energy. And if I raise those, I can see it changes the rate. But now I've got a reaction that's favoring making more B. It's favoring the forward. This would have like a, hey, it's making and breaking at the same rate. It's reached equilibrium. And this favors more B because this is the downhill battle. It's lighting something on fire, right? Nature loves to, of course, light things on fire. It doesn't like to build houses. It likes to burn them out. Downhill battles, right? Cool. So if we look at this, let's capture some main ideas off of that. One thing we can see, of course, with those reversibles is some handy stuff. If I look at this, of course, this is an easy reaction. There's no activation energy. A is going to get turned into a B until it reaches a nice equilibrium of 50 and 50. If I raise the ruler, I'm changing the amount of activation energy. I'm making it harder to break those bonds. If they're too hard, that's a stable compound. Hey, it has a high activation energy. I can also, of course, raise the stage, which changes the amount of potential energy in the system. The higher it is, the more potential, the less they move because that kinetic is turning into potential, just like running up a hill, right? Now you can fall down it. That would be an exothermic reaction right there, right? Cool things I can also do with this is I can change what the reaction does momentarily. I can make more B if I want by doing a couple things. I can add more A so they collide more often. I can increase the amount of energy so they collide more often. I can heat it up. Or I can decrease the activation energy. I can use a catalyst. And that's exactly what a catalyst does. This is, of course, an endo or an exo. Well, the forward reaction would be an endo, an uphill battle. And that's why this reaction is favoring the reverse reaction, the exo. It's making more A when it reaches equilibrium. It always favors the exo, right? It's easier to turn stuff into heat than it is to store it in bonds. Then, of course, there's this beautiful thing called a catalyst. And the catalyst basically changes how easy it is for a reaction to happen, how it lowers the activation energy so things can collide in the right position more often and more easily with less energy input. What that means, of course, is that we use these like crazy, like in catalytic converters in our car to make reactions happen that we want to happen. We use them in pretty much every chemical process on Earth. Catalysts speed up reactions, but really what they do is they lower activation energy so that it takes, of course, less energy to have a reaction happen. They increase the likelihood of it. By dropping it, I can make a lot more A, right? I can also make B. So it affects in both directions. Now, this you should write down in your ETD because it's pretty much the essential part. And this is about understanding energy diagrams. You can guess that we test you on these because, of course, colleges love it, and it is how the universe works. It's all about energy. Now, you should have two different types of energy diagrams. One that's a downhill battle and one that's an uphill battle. A good example of this one is we can see it's at a high position, so it has really high potential energy. That also means that it's likely to have low kinetic energy because most of it's stored inside the bonds. This would be my reactants. This is my products. You can see I'm going from a high potential energy, a lot of energy stored in bonds, to a low potential energy, which means more of that got converted into kinetic energy because it can't just disappear. And that means, of course, to do that, energy is going to have to get released. Hey, that would be the easiest form of energy, heat energy. And light energy, of course, can get released too because this could transfer electrons. To do that, though, you have to have a little bit of kick to get it going, just like you put a match near a fire. It takes a little while to get it started. That, of course, is the activation energy, E sub A. And activation energy, of course, can usually be supplied with heat because we can add that to it, right? You add heat to get that reaction going. This is a downhill battle that's releasing energy, so this is exothermic. And being exothermic, of course, it's going to release that extra energy as it doesn't have to store all of it in bonds. The easy way to do it is to turn it into heat energy. A good example of this would be something that's high in energy, like something we crave, like sugar. Its bonds have high energy, high position electrons that we then burn and drop down to CO2 in this wonderful process called cellular respiration. Or you can do it by taking a log and burning it, because the log's made out of sugar too. Or a marshmallow if you want, right? So cellular respiration, of course, is how we get our energy, because we like a downhill battle. It gives us extra energy from our food items. That's why we crave them. How did that energy get in there? Well, that's the beauty of this thing. There were some reactants called smoke in the air, CO2 and water. And these amazing things called plants turned them into sugar. Marshmallows originally came from a root that was in a marsh. It's a marshmallow, right? And if we look at that, that becomes the products. But to do that, it's going to take a lot more activation energy, because this is an uphill battle. This would take something that's at a very low potential energy and increase, of course, the amount of kinetic energy if you especially add heat energy, right? You're going to force it to go uphill to get to the other side. That would put it in a new position where the electrons are high and far from a nucleus. They have high potential energy and would likely reduce their kinetic energy because it's being stored inside of it, because it's got to go from one to the other. Now, key thing is, this would be an uphill battle because you have to add energy to it. And if you're adding energy, that is an endothermic. This thing is going to store energy in sugar. And who can do that better than anybody? Whether these crazy critters called, of course, plants, and they take light energy for their activation energy to do a thing called photosynthesis. Hey, they boost up the potential energy and we drop it down. Of course, they do it just for themselves and they don't need us, right? Key questions that we should understand with that is, how do I make more products? Well, it's easy. One of the things I can do is I can change, of course, the amount of heat energy. If I do that, if I add heat energy, I can get it over its activation energy. And that's what plants are doing. They can add heat or they can add light, but that's why plants grow so well in the tropics. So think of things like photosynthesis, right? Also, another thing I can do, I could, change the amount of reactants. If I wanted to force it forward, I could add more reactants. That means if I add more sugar, I'm more likely to have more sugar broken and get more energy. That would, of course, increase the amount of CO2. Or I could increase the amount of CO2 like we've been doing on Earth and cause more of the endothermic reaction, right? Because this is reversible. That would be photosynthesis, and this would be cellular respiration. We burn the sugars and burn the trees, and they stick it back into trees, and then we burn them down. If we were smart, we'd figure out that we need a balance of those things to supply us with enough sugar and oxygen to survive the rest of the human civilization's time, but we'll see that. Remember, it's about more collisions of the reactants. So right now, some plants, of course, are doing photosynthesis faster because there's more CO2. Too bad they could solve our problem if we'd stop cutting them down. Not that this has anything to do with real life. It's just chemistry, right? So if we look at the third part, it's really crucial. It's what plants are the master of. They use this beautiful stuff called chlorophyll because it changes the activation energy. It lowers it because it's a catalyst. That's why there's a bunch of enzymes in your body that break things down. That's what doctors learn most about in AP Bio. And plants use enzymes as well, especially this wonderful chemical called chlorophyll, to help get the electrons in a position so they can add energy to that water and bring it up and make it into sugar, right? Sounds like this has something to do with real life. Nah, just chemistry, right? Now, get out your notes because you're already taking them, right? Now, if we look at this, you should write this down. A catalyst basically lowers the activation energy. You can see I have this really high activation energy. When I add the catalyst, it drops it down and makes it easier to go through the forward and the reverse reaction. They favor both sides, but of course we can see that this would favor the reverse reaction because it's exothermic. But it makes it easier to do either way. In biology, catalysts are called enzymes, and they end with words like ACE. We talk about enzymes like crazy. It's how you get a MD degree, right? So catalysts, very handy. They lower activation energy. They make it easier to, of course, make the products and the reactions collide. Most of your life is spent building enzymes so you can do reactions easier because you are a chemical reaction. Here's a chemical reaction that you should write down. I wish I could demo it for you, but I'll have a little video clip that'll show you how it works, basically. This got this stuff from the ETD called N2O4 gas, and it can be made or broken to make NO2, right? It's a reversible reaction. Now, cool thing about this is, no pun intended, the ice bath is I can take this tube that has this N2O4 in it, and if I stick it in the ice bath, it turns a nice golden color, meaning that I'm making more N2O4. If I take it and I stick it in a hot bath and add energy to it, I will produce this brown stuff called laughing gas, NO2. Now, the good thing is it's inside of a tube, so this thing is a closed system. It can't escape, which would, make us laugh and then kill us because it's toxic, right? As we do this, our job is to figure out which direction is endothermic and exothermic. I can simply take these tubes and move them back and forth, and when I do that, they will go from favoring one side or the other, from golden brown to nice dark brown, or nitrous oxide, right? So, it'd be nice if we could see this in person, but the basic idea is this. When we stick something in ice, the ice feels cold because it's stealing heat from us. When we put it in a hot bath, we're adding heat to it. So to get to that part, you actually have to add energy to it. So this means that we're adding energy to this side. The ice bath is stealing it away from the NO2. That means that this direction, of course, is the direction where you're building up. You're adding heat energy to it. That is my endothermic reaction. When I take it and I remove it, I add the heat to it, that, of course, is helping to break it, and then it releases that into the ice. That's the tricky part. The ice feels the heat from it. That's the exothermic direction, which makes sense. The heat is on that side. And that's crucial because one thing we've been not adding to our reactions is energy. And energy needs to start adding up in your chemical equations. If I turn this into an energy diagram, it's pretty easy to do that. The forward reaction is endothermic, so it's uphill. And it would look basically like this. The N2O4 needs extra energy to get up to this thing called NO2. That heat energy supplies the activation energy. That's what's going on in the reaction. So that means I should add it into my reaction. Hey, look at that. I wrote a correct equation, which should now include energy when you write it. This direction, of course, is my exo because it's releasing heat energy. This direction, the forward, would be endo because it takes energy to get uphill. Wish I could show you in person, but coronavirus. Now, this is what it actually looks like. Here's my N2O4. It's nice golden brown. If I add heat to it, that will make it collide and rip apart, and it will become NO2. That NO2, of course, will rip apart itself as it collides and produce heat and this more stable compound as it goes downhill. Now, here's a different reaction. I wish I could show you, but it's a basic idea of this. I'm going to take some barium hydroxide, solid, and I'm going to mix it with some ammonium nitrate, solid. You should be able to predict the reactants of what this will produce and then decide if it would be exo or endothermic. Now, key thing is you should notice, hey, a solid is solid, that's not going to react. Well, the key thing is this barium hydroxide actually contains water. It's a hydrous form of it. And the way we write that is there's 8 waters for every barium hydroxide. Or you could just add a squirt of water because the water makes it easier for them to collide. It's almost like water's a catalyst. But that's why we spend so much time talking about water. It speeds up reactions by making them dissociate. They're more likely to collide, right? Now, good news is I got a solution, and I have another solution to mix, so I could do the old switcheroo. And if I look at things that are inside of this, well, there's one thing that's right there, and it would be very stinky. It would make this stuff called ammonia, which would split off and become a gas. There'd be 2 of those, right? It would also produce a lot more water, which makes sense. There's an H there and OH there, so that could produce H2O, because the universe likes to make water and gases, right? It's like driving forces. There'd be 2 of those. At the same time, I got this barium thing with a 2+ and a nitrate with a 1-. Hey, that could make this new thing called barium nitrate. That barium nitrate actually is just spectating. It is aqueous, right? Because without another -2, it's going to stay in a solution. And included with that, I would, of course, have to add 2 of those to balance the whole thing out. Now, the neat thing about this is when you do this reaction, it stinks, it makes water, and it makes a white liquid, but it also feels cold, which means that, of course, if it feels cold, it's taking in energy. So that means that this would require heat energy to do this. This would be a forward reaction that is endothermic, and it feels nice and cold. In fact, it's cold enough that we put these things in ice packs. And if you've ever been at a game and you hurt your knee and they get out this weird pack and they crunch it, and it suddenly starts getting really cold, that's because they're using a chemical reaction that's endothermic to suck up the heat from you. And what it's doing is it's producing this wonderful old switcheroo, right? Now, key thing, of course, is that cold pack doesn't have an arrow that's going both ways. I thought all reactions were reversible. Well, they are, but the trick is this is not a closed system. It's allowing something in and out of it. It's allowing out heat. And in a beaker, it will actually allow out the gases, which means that they can't collide again. So that's why the hot pack or the cold pack does not always last forever. If you use a hot pack for something, well, that's an exothermic reaction. So pretty cool experiment. Wish I could show you in person, but that's life. Dum 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 dum. Vanilla ice, ice, baby. Cool. That guy does look familiar. I love the pants, right? He never ripped off that song. Totally. Now, you're going to like ice problems because they're really, really easy, right? So let's go into it. Let's say that I got a simple problem. I got A plus B makes and breaks C. You should write this down so you have it. This reaction starts with those concentrations. Your job is to figure out what's the concentration of A and B at equilibrium when they meet that magical spot where they are making and breaking, right? So write down the question, pause me. Wish I could pause. And here's how we solve this. It's very, very straightforward. First, you write down the equation. A plus B makes and breaks C. It's a reversible reaction, as all reactions are. And how do I solve this? Well, I get out my ice box, baby, right? Vanilla ice, ice, baby. And an ice box is literally a box that you're going to use. And it has a couple things in it. The I stands for initial. So these are their starting concentrations. The C stands for this wonderful thing called change, because you got a reaction. They're changing. And then the E, well, the E stands for equilibrium, right? Their equilibrium concentration. So I set this up like a simple math problem, and I look up. And I can see that right here at the start, the initial, I've got 0.5 molar of A, right? Moles per liter of A, because this works for concentrations, because if you put solutions into an ice box, right? Not just moles. If we look at the B, it's 0.3 moles per liter of B, right? And then it tells me an important thing. It tells me at equilibrium, there is C. It's 0.2 moles per liter of C, right? Now, key thing we should notice, it's basically that you can assume that at the beginning, this reaction hadn't happened because there's no product, so there is 0.0 moles per liter of C. So that means that something has changed, right? Now, obviously, we can see this went from 0 to 0.2, so that means that I made 0.2 moles per liter more of C. It went up. Hey, that's crucial because the multimole ratio tells you that for every 1 C you create, you destroy 1 A and B, which means that you take away 0.2 moles per liter of A and 0.2 moles per liter of B. Hey, and then you do simple math. 0.5, 0.2, it's 0.3 moles per liter of A and 0.1 moles per liter of B. Hey, look, that's their equilibrium concentrations. This is when they are making and breaking each other at the same rate. And the key thing is they've met their balance, right? Oh, it's almost like some things can be easy in chemistry. Let's try another one, a little more realistic, right? Vanilla ice. We're going to practice this ice problem. I got A plus 2B makes and breaks C, right? Ooh, freaky. Here's the initial concentrations and stuff that you would need. Pause me. See if you can solve it with a ice box, baby. Cool. If we go at this together, first thing I do is I write down the equation. A plus 2B makes and breaks C, right? I'm going to get out my ice, baby, because it wants this thing called the concentrations at equilibrium. So my initials that I can write down, I've got initial for A is 0.4 molar right there. I've got B is 0.3 molar, and I haven't made C yet because it's the product, so it's 0.0 molar of the C stuff, right? If I look at the other info it gives me, it tells me, hey, I made some C. It's 0.1 moles per liter of C at equilibrium. Okay, I can live with that. That means that there's been a change, right? And if we look at the change, it went up 0.1 moles per liter of C. So when I do that, simple math, right? Now, the good news is for every C I create, I destroy an A. So that means that, well, if I made 0.1, I have to destroy, subtract 0.1 moles per liter of A. When I do that, the thing I will notice is it's 0.3 moles per liter of A. It had to go down because I'm making C. Then I see that it takes 2 B's for every 1 C. So I have to destroy 2 of those B's. That's 2 times as much. So I multiply by 2. And it's 2 times as much of C, so it's 0.1 times the 2, which is 0.2. And then I subtract it, and I'm left with 0.1 moles per liter of B. Hey, look, they reached their equilibrium concentrations. Doom, 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 doom. Vanilla ice, ice, baby. Yeah, kind of sounds like a David Bowie song. Cool. Under pressure. Cool. Normally, we would go after the icebox worksheet and figure out that KEQ is the same thing as KC. Instead, you're going to do your remote learning part, but like them pants, Vanilla Ice did have some good moves. It was all in the ice box if you're looking at those concentrations. Our target today was to figure out how to use ice boxes with problems that are very, very simple of looking at their equilibrium concentrations and to gain a better understanding of how these things called energy diagrams work, looking at the amount of potential energy versus, of course, the kinetic energy. This has a lot of kinetic or potential and very low kinetic. That will be converted into lots of kinetic, known as heat and moving particles, and less potential. Hey, that's a downhill battle. It's exothermic, but I can go either way. Notice that when you write your equations, that would mean that you'd have to add heat energy to the side that is the product side, because we need to consider energy as well. There's my reactants, there's my products, right? All right, take it easy. Don't be afraid to, do a little dance.